Oh, welcome back, everyone. Nice, bright, sunny day out there. Not? Okay, so last class I posed this question to you. I asked, well, you've got to, if you have a compressed column matrix, suppose it's, I don't know, 5 by 20. Okay. So I've got 5 columns listed there, 0 through 4, and but it's the row indices are unsorted. Okay, and so this is not at all related to the project, by the way. Oh, I should add, in the project, when you're sorting those tuples, your comparator function, if you have say a row index and a column index and a value. Okay, then if the columns differ, then of course this one comes before that one. But your comparator function should do the following. If the columns match, right, then you use the row index. So if this is, so if you compare these two triplets, then the rows are the same. So to break the tie, you'd have to check the, I'm sorry, did I say rows are the same? I did, didn't I? You could rewind that tape. And the columns are the same, so you check the row indices to know which comes before which. And of course, if those are equal, the compare function to return a 0. Because if the row and column indices are both equal, your qsort compare function should return a 0. And as a result, then, in this matrix, if you have duplicates, which, by the way, you do not have to worry about in this project, okay, you can ignore that. I mean, you can provide input data that is unsorted, but it's with no duplicates. And so to do that, if you do ijx equals find, I think I explained this, p equals rand perm nnz of a. So you get a random permutation of length, the number of non-zeros, and then just permute all these guys. So that provides a really good test input for the project. You've got this list of triplets now; they're all jumbled up, and you've got to then create a sparse matrix, and then you can compare with this matrix to see if it's in fact equal. Okay, but in what you're doing, okay, when if you did have duplicates, it'd be a lot simpler because now all duplicate entries would be adjacent to each other in the columns, and so you could just look at 2 entries and say, okay, let's just take this band of values here, which will have all the same row and column index, and just compress it down to 1. So that would be really simple. And it's very simple, of course, to compress data in place, right? If you go through a list and you decide, I'm going to delete all the negative entries, or entries for which some predicate is true, right? I mean, you can do that in place quite easily, of course, right? You just go to an entry, and if you want to keep it, you copy it from where it is now to a pointer or an index that tells you where the last one is. And so if you don't want it, then you just skip and you increment, right? And so it's very simple to compress a list in place, right? You should know how to do that, so I won't belabor that point. But I'm going to use that idea here, that each of these columns I'm going to compress in place. I want to remove duplicates, sum them up in place. And I don't want to create a new copy of the matrix. So what I want to do is, suppose there's duplicates in here, this column will be shorter as a result. So that when I process this column, as I find valid entries, I will append them to the end here. So you get this great big long array, right, of the row indices and the column values. One column gets shrunken, and so when you're let me draw this out this way. So you go through this column and you prune off those entries. And then as you're searching through this column, if you find a good entry, you shift it up above to here, right? So there's a pointer or an index that tells you where you currently are in the input and then where you are in the output, which is overwriting the input. But it's okay because the output always trails the input. So I'm going to use that here, but still, we're going through these columns then one at a time. So that doesn't quite fully answer the question. We're going through these columns one at a time and in place. And I've got duplicates here. So for example, I might have a row index 5 and a row index 5 and a row index 5 and a 1 and a 1 and a 2 and a 2 and so forth. And my goal is to produce, in fact, what I will end up producing is a new column. If that was the total column, suppose this is like, maybe there's an entry that's not a duplicate. What I want to produce then is a list that will look like this. It'll be in that order. It's still unsorted, but it's got no duplicates. So that's the goal. And I made a claim that I could do this in linear time, so that without doing a sort and doing it in place. So did you think about that problem? Of course, you could look ahead in the book and see how I do it. But did anyone? It's really, once you see it, it's like, oh, of course, that's a cute trick. But a lot of sparse matrix algorithms are like that. There's sort of two parts to sparse algorithms. Well, there's the matrix computations. They go along for the ride. But there's really two aspects of sparse matrix algorithms. One is all the beautiful combinatorics and the theory that goes behind and some of the algorithms that go behind it in terms of really it's applied graph algorithms. Okay, but the other part of it are very subtle algorithmic tricks like what I'm going to show you here that if used carefully can have a huge impact on performance. So these are they are algorithmic things. They're solving simple problems, but if they're done wrong, you can spend a huge amount of time solving them. So any thoughts on how to do this? No one's gonna.
Can you use hashing or something?
Hashing? No, I don't use hashing. Well, not really hashing. No. But you're along the wrong. You are on the wrong. You are along the not wrong. You are along the right track. Okay. So here's the idea. I have a workspace W of size M. So if this is, oh darn it! Look at that. Look what I did. Look at the size of this matrix. See, I told you. What's wrong with my brain? I don't know. It's 20 by 5. Oh, I should add, by the way, if you come from an Asian subcontinent for which my home state of Indiana is named, it is, by the way, Indiana. It's named after your country of India, indirectly through a mistake, right? If you pronounce that in Indian English, that's 20 by 5, isn't it? Yeah. And us poor Americans are completely confused. Because we think 20 by 5, we think maybe a matrix of size 20. We don't use the word by. And so that when I say by, I don't mean this. All right, I'm speaking English of the American variety, not English of the Indian variety. Not that one is better than the other, they're just different. Okay, so 20 by 5 matrix. So I have a workspace of size 20. Okay, and it's going to start out, all these values are going to be -1. And what this is going to do is going to keep track of me for me for a given row I. It's going to be an index into AI AX where row I was last seen in any column. Well, but I can't add a row I in column 3 to a row I in column 4, 2 or something, right? I mean, that doesn't make any sense. And I should add in here the new. An index in the new AI and AX array, that is the one that's being compressed. It's in place, but the new position of this row in whatever column it was last seen in, that's the position where I last put a row I. So the ith entry keeps track of that for me. And so suppose, let me put some numbers here. Suppose I've got, say, 5 entries here and 3 entries here and 1, 2, 3, 4, 5, 6, 7, 8 entries here. Okay, so what are my column pointers? My column pointers are going to be 0, or my column indices, right? 0, 0, 1, 2, 3, 4, 5, 8, 16, and so forth. This is going to be the position of where, within these two arrays, AI and AX, of where those columns start. Okay? in the input array. Let's suppose there are 2 duplicates in here somewhere. And maybe there's none in here. Okay. So what's going to happen is, and let's see, maybe I'll not put duplicates here. Maybe I'll just leave this so we can just focus on one problem at a time. Okay, so now I'm at, suppose I process these columns. Okay. And I keep track of where I see, say, row 2. Okay, it's in position 0, 1, 2, 3. So in what I'll do is every time I see a row index, I'll log that position, overriding the previous value. I will log that position here. Under 2, I'll put the position 3. So then the next time I come to a row index that's value 2, I'll look this value up and I'll do something accordingly. Now, if I'm at this column and I come down here and I see a row index, I should have started with 1, not 2, but if I see a row index 2, okay, and I look it up, well, where did I last see row 2? Oh, I saw row 2 at position 3. Oh, well, that's not a duplicate because my column currently starts at position 8. So row 2 is at position 3, so it comes before that. So it's not a duplicate. This is a unique value. But now I'm going to log this position. Actually, this position will have gone away. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. What's going to happen is when I'm done, I'll decide, okay, this is not a duplicate, and I will end up putting it in, I will move it up to position 10 because this will have been a duplicate. I've already will have processed that. Maybe I should have done this one first. And when I'm done placing this row 2, I'll change this to an 11 because that's the position where I saw the last row index 2. Now, if I come across another row index 2 in the same column, here, another row 2. Let's look up, see, where did I last see row 2? Oh, I'm sorry. No, I'm going to put a 10 here because I've moved it. Row 2 would be now here because it's going to be in the final analysis. This is the result for column 0, 1, column 2, the third column. That's why we start. That's why mathematics starts counting at 1. You know, to say column 2 is the third column sounds kind of weird. But anyway, counting. We're computer scientists, so we start with 0. We count with 0. Like, how many fingers do I have? How many fingers do I have? Yeah, answer the question. 2. No, I have 5 on this hand. Only 2 are extended. Okay, so we can't count. So I have a 10 here. Okay, so the next time I come down here and I see another row index 2 at position 13, which I don't really care that it's position 13 at the moment, but I look up 2 and I say, the last time I saw 2, row index 2, I put it in position 10. Oh, but 10 is greater than or equal to 8, and 8 is the start of my current column, and so this is a duplicate, so I have to sum it up. So where do I sum it up? Position 10. This tells me 2 things. This number 10 tells me 2, 3, 1, whatever. It tells me 2 things. It tells me if this value is less than 8, I know it is not a duplicate. 8 is where this column starts in the output. If this value 10 is greater than 8, which now it is, then not only does it tell me it's a duplicate in the current column, it tells me where row 2 is in the current column. So I don't have to go searching for it. So you mentioned this, hashing. It's kind of like that, right? This is like your hash table, your hash bucket. Okay. But you only have to, there's no hash collisions. You only have to record one thing for any given bucket. Okay. So when I come to this position here, I see a row 2 and I don't have a column 2 and row 2 and there's a numerical value. Okay, this is a duplicate. So what I have to do is I have to go to this position 10. I'm not going to change this value 10, but what I'm going to do is I'm going to delete this entry and take the numerical value and add it to AX of 10. That tells me where to do the summation to sum up the duplicate. Isn't that cool? Very simple trick, very simple algorithm. But it's exploiting the fact, and we do this over and over and over again in sparse matrix computations, and again also in graph algorithms. It's very easy to have an array of size n if you have n nodes in a graph for various workspace and informational kind of things. Yes.
This is going to have a space complexity of O of n, depending
on yes,
M.
That's correct.
Wouldn't it be better if, since we are dealing with larger matrices,
right?
Wouldn't it be better if we use an O of n square algorithm like
n squared time?
N squared times this?
No, you can never. N squared time is verboten. That's German for don't do it.
I can think of simple techniques where I can pass the array once and.
Well, yeah, we never want to do n squared time. The question.
Sorry, m squared.
M. I'm sorry.
I think I'm a little confused about it. Should be n squared, n into n, some kind of that kind of complexity.
Oh wait, now I gotta forget the Indian English here. This is
sorry.
m into n, right?
Yeah.
Okay. We call it m times n. Sorry. Yeah. When we use the word into in English, like you divide 2 into 3, it's a division. So the into is a divide, and by I think multiplied because the matrix is 20 by 5. So it's completely. So a poor dyslexic like me, when I'm faced with Indian students, I just get completely deranged. Not that I'm already deranged, but I get even worse. No, we don't. We can never afford time complexity of order mn. Okay, this is not a sparse algorithm. Period. Okay, so we can't afford that. We can afford, say, m log m or n log n. That's not so bad. Or k log k if I have k non-zeros. Those aren't too bad. I can afford an extra logarithmic factor. This is nasty, actually. The logarithmic factor is not so great. It can cause a lot of problems, and I have MATLAB users coming to me and, oh, my algorithm's slow. Well, it's because MATLAB is using one of these, and use something else instead. So even logarithmic is not great. It's because it'll eventually really kill you. Most of the algorithms you see here don't even have a log term in them. In fact, I can't think of any where I actually have a logarithmic time complexity. Polylogarithmic, I mean, or n log n type. So no, this is completely out of the question. This is more this is what you're doing in the project. Okay, so it's not so unreasonable. I don't do it in the book, but you can. Okay. But no, we can't do that. So n squared or nm, mn, or whatever is way too much.
Is it safe to say that in general space, like memory, is cheaper than time? Is that what you're getting at?
The comment is memory cheaper than time. No, I don't mean that. And I'll elaborate. But you have another question? Is it similar? Or?
Is that the time complexity of that particular algorithm is linear?
It's going to be linear, but but let me explain that when I'm done describing the algorithm. But let me answer. It's Ed, isn't it?
Ed, yeah.
Let me answer Ed's question. You had a question to repeat was about time complexity. Let me finish the algorithm, and then I'll answer the time complexity. Let me answer Ed's question, though, because that's more general, not specific to this algorithm. Kind of like Debbie's question was more general. And I'm sorry, what's your name again? Your name again?
Imnath.
Imnath?
Imnath.
Imnath. Okay. Now it's on tape for everybody to know. All right. Too bad the camera can't pan the class. You know. Okay, so time complexity and space complexity are both important. Okay, this kind of time, space, and memory, I said that, time and space complexity is fine. Okay, if the matrix is m by n with k non-zeros. Okay, certainly you have to store the non-zero values. So this is, and you have to work on them. So this is pretty much given. You've got to work on them. And most matrices have at least one non-zero in any given row in any given column. Why would you create a matrix with a completely zero row or a completely zero column? All right, if you have a linear system that you're trying to solve, then your matrix is, you don't have a solution. Okay, so but there are cases where you do have a sparse matrix where you have zero rows and columns. But if you don't, which is often the case, then m and n are going to be less than k. So if you have order k space, you can afford order m workspace and order n workspace and m and k time, because asymptotically they go away. If every row and column has at least one non-zero, then m is less than k and n is less than k, and so you just have k. Now there are exceptions. There are exceptions to this rule. And the bioinformatics toolbox in MATLAB uses that exception. It creates, it basically wants to use a sparse vector as a hash table. It has a billion entries it wants to just stick there. It's like, well, here's the 5,976,000th genome or whatever. And it just sticks it in that, or they just stick it in an array like a hash. They're treating a vector like a hash bucket, basically. Just stick it there and then just get it out. It's not being used as an algebraic, as a linear algebra object. It's being used as a data storage bucket. Stick it there and get it out. Okay. And so it's got a lot of empty rows and columns, empty rows in it. So m is dominant in that problem, and k is not. All right, so there are cases where this is a problem, but still, doing this is most of the time not too bad. And certainly if we have this data structure, now this is not the only possible data structure for a sparse matrix. Okay, every graph, if you will, would have to store at least every edge. Okay, so it would be order k. We have k edges. Some representation of each edge. But you would not have to store a representation of each node. If you had a node with no edges, you could just not store any information about that node. Like the triplet form does that. Right? I could store just a list of triplets, row, column, value, row, column, value, row, column, value, row, column, value. And I could say, if I could have 5 non-zeros in it, and I could tell you, oh, the matrix is a billion by billion. It's got 5 non-zeros in it. I just list the 5 there, and we're done. And I've taken order, 5 space, plus 2 integers that tell me how big the matrix is, just for fun, if I want to know. Okay? It could be infinite by infinite, and it's still okay. So m and n would not have to be there. But m and n in most cases are acceptable. Okay, so I've got m workspace here, so that's acceptable. Because if I make the simple assumption that k is bigger than m, then this is not asymptotically dominant space or time. Okay.
But you said that it will be done in place.
I'm sorry?
But it is not in place.
It's not what?
In place.
In place. Oh, okay. When I say in place, yes, I do mean I don't mean this right here. Yeah, I allocate a little bit of extra workspace. So if we assume that m is less than k, or sometimes much less than k, usually m might be on the order of 10 or 20 is typical. Okay. When I say in place, I mean the matrix itself. Usually, most of the time, you're going to need a little bit of extra workspace of size m or of size n, and some small multiple of that. So when I say in place, I don't mean this extra stuff, this temporary workspace. I mean the matrix itself, where K is usually the dominant term. So I'm not making a copy of the matrix, but I do have some extra space here. So in that sense, yes, it's not in place. You're right. But I'll use the term in place for this kind of algorithm. But if I had to make a copy of this into another matrix, then I would call that out of place. Okay. So that's the gist of the algorithm. And so let me show you the details of the algorithm here, just in the code. And so you see here up to this point all the standard stuff of checking the input, getting the input components, allocating workspace, returning if we don't have an input or if we don't have workspace. And so at this point, this for loop starts the real algorithm. All right. So the first thing I do is I set my W array to all -1. So already now I have an order m time complexity. Then I'm going to go through every column. Now so I've got order n time complexity just by this loop right here. So the time complexity is already m plus n. Then what I do is I have a pointer or an index q that tells me, see, nz starts out as 0. This is the number of non-zeros in the output matrix, which is being overwritten, which is overriding the input matrix. So this is keeping track of how many entries there are in the pruned or the compacted matrix. So I'm going to go through the existing. So AP of j and AP of j plus 1 have not yet been modified. So these are now referring to indices for the old matrix, not the new matrix. It's compacted. And remember, it's being done in place. It's overriding the new as we're overriding the old. So I get the row index, and I'll look this up. I'll say, well, hey, is Q right here is keeping track for me of where this column J where it starts in the new matrix. So if I've had no deletions yet, and let's suppose I have no deletions up to column 8, then Q is just simply equal to 8, because I have 1, 2, oh, I lied. 6. This should 5, 6, and 7. I didn't count right. That's all that counting at 0, you know. It just 8, 9, 10, 11, 12, 13, 14, 15. There we go. I'm sorry, I counted wrong. Okay, so Q is 8 at this point because I've seen 8 non-zeros that I've kept. NZ is keeping track of how many non-zeros I've kept. So Q equals NZ. NZ is going to be incrementing, so I want to keep track of Q, which is the start of this column. So I look here and I come across a row index. Let's say I come across first I'm going to come across a row index 1. And suppose I last saw row index 1 back here at position 4. I come across this row index 1 and I look at W of I and it's equal to 4. So it's greater than equal, so it's less than Q, it's less than 8. And so it's not a duplicate, it's a new entry. It's unique to this column. So I store where I'm putting it. So position 1, I put an 8 inside W, because it's right here. And then I go and say, okay, put the row index there in that position. So put a 1 here, which may actually put it in the same place. So I write a 1 there, and I put its value right there, right next to it. And I increment my count of the non-zeros. So now when I come to 7 and 5, I do the same thing. But now I come to this position 1 again. Or I come to a row index 1. I see it again. And when I see it, I come over here and I say, row 1 is in position 8. But 8 is within my current existing column. And so what has to happen is this is a duplicate then that has to be summed, and that value W of I tells me where to sum the duplicate into. So this is the case that it's a duplicate in the same column, and this is the case it's unique to the column. In this case, NZ does not increment it. In this case, it is. When everything is finished, and so you just keep going here, and you're going to be overwriting. W of 1 will be 8, and W of 7 will be 9, and W of 5 will be 10, and so forth. Now when I come to this 2, okay, I look at position 2, and I'll see what will I see? A 3, I think I said. 0. I last saw row index 2 at position 3. 3 is less than 8. 3 is less than 8, so this is false. So I come down here, and I put an 11 here. Okay, because NZ was not incremented the last time. So NZ is pointing to this position, because this entry was a duplicate, so it got shifted up here. So NZ is where I'm going to put the entry 2. It's moving up by one entry. It's moved by one position in the array. So what's going to happen is this value here is going to be put here. And this is now empty space. And write an 11 here. So now I come to the 5 and I say, oh, 5 is in position 10. So I'm going to remove it from here and add it to this thing. And NZ still points to here. No. It's been incremented. NZ points to the next empty slot, if you will. So NZ is pointing to here. It's the position to put the next entry in. I'll come to here now and I say, this is a duplicate, so I sum it here, and I change W of 2 to 14, and so this is now garbage. Then I'll come to here and I'll see a 5, and I'll say, 5 I've seen already, so I'll remove it, and I'll put it, and I'll sum it to here. And so now NZ points to this position, which is exactly where I want it. The index NZ tells me where to put the next entry, which is going to now be in the next column. Which is why I start here. Okay, column J will start at Q when I come to the next column. Is that clear? Once you see it, I mean, it's a very simple algorithm. It fits on a slide even. Every last detail fits on a slide. There's a lot of loop, what's the word I want to use? For proving an algorithm correct, you have a conditional statement that's always true at a certain iteration of the loop. There's a name for that. Invariant. Thank you. A loop invariant. I couldn't remember the word. It's a loop invariant. So I've got lots of loop invariants here that I'm relying on. And if this were my commercial quality code, I would put those in there as assert statements, all kinds of places that would sort of be like executable comments that are telling you about how the code is working. But this is a clean and concise code, so I don't have those. One thing I do then at the very end of the jth iteration is I have to keep track now of where the jth column starts, which is Q. And then ready to go to next column. So I'm overriding the column pointers as I go. But then when J increments, AP of J has not yet been changed, and AP of J plus 1 has not yet been changed. So this is still indexing the positions of the old column J, not where the new one will be. At the very end then, I have to do AP of N equals NZ. This is a common mistake to forget this sort of thing. At the very bottom, you've got it at the very bottom. 18, 19, 20, 21. You've got to make sure that AP of N is equal to, say, 21 if there are 21 non-zeros in it. Otherwise, you'll fall off the end of this last column if this is undefined. It's a very common mistake to leave this out. So as you're working on the project, of course, you have to construct these column pointers. Where does each column start? Well, don't forget to tell where the last column ends, which is this one. Then I free the workspace and return the Sprealic matrix A. So what Sprealic is doing, it's the sparse realic, if you can see it there, is it's taking my sparse matrix A and a parameter 0 tells me to make the matrix concise. That is, just make the NZ max equal to NZ, the actual number of non-zeros. Trim off any excess space. Because presumably if there's any duplicates, I will have excess space at the end of the matrix, and I want to just trim that off because maybe I can use that memory for something else. And if there are a lot of duplicates, then this could be very helpful. If there's only a few duplicates, this is useless, but it doesn't hurt to have it. Because usually this kind of memory management operation is not very costly. If the memory manager can't use that extra space you free up, it just marks it as unavailable, and it's fragmentation. That if you then free this whole matrix, then that space becomes available. But it's usually constant time to Sprealic something smaller anyway. And if you save a lot of space, if the malloc manager decides, hey, you just went from 1 billion space to 1 million, oh, let me move this somewhere else, then that's probably a good idea anyway. And you have saved memory. So now to answer Anath's, no. And I'm sorry, your name again? Anath? Emeth. Emeth? Okay, Emeth. To answer Emeth's question, what's the time complexity? So we have here a time complexity of m, because we've got this initialization. We have n, because we go through each n columns. And then we've got a loop here that it's iterating across these statements here are executing once per non-zero in the matrix. And I use this notation, right? I put the size of, which means the number of non-zeros in this matrix. That's the notation I use. So that's the time complexity. The memory complexity is order. It depends on how you want to think of it. The memory complexity, the space complexity is just this. Oops, no. And because this is the space for the original matrix that I'm operating on, it's only order m additional space I'm using. So the time and space complexity are the same, and it's essentially linear time. In other words, so it's linear in the size of the problem, sort of. But I'm really lying when I say that. Because if I were to say it's strictly linear in the size of the representation of the problem, I would have to say it's n plus a. But it's not. It's got this extra piece in there. So if m is dominant, if you've got a matrix with a few columns that's 1 billion by 5 and it's got 20 non-zeros in it, then this loop here is going to execute 1 billion iterations, and this is going to kill you right here. This is where all the time is going to be spent, just initializing this vector to -1. And all those entries, most of those entries you won't ever see, which is kind of a pity, but that's life. If there were a way of, you could imagine a virtual memory system that could do this, right? I could tell the memory manager, give me an array, give me a memory space of size 1 billion. Don't initialize it. But the moment you have a page fault to an area and you bring in the page in, set that page to a certain constant, all the entries in that page to a constant value. They could do that, right? The memory manager, a virtual memory manager could easily do that. And then what I could say is, look, allocate this space and let's pretend it's allocated to some initial constant value, 0, -1, whatever. I could, if I had to use it, if I had to initialize it to 0, I could still do that. I would just offset it by 1 when I use it. That's not a big problem. But let's say it's 0. Let's suppose you have a calloc. Let's suppose the virtual memory manager could say, allocate this enormous space that may dominate your whole virtual memory space, 20 terabytes of data. Okay, and initialize it all to 0. Well, let's just pretend to initialize it to 0. Let's just state, okay, if you have a page fault on this memory space into an area which you've not seen before, then at that moment clear that space out to 0 in physical memory. That would be, if I had such a thing, if I had such a memory manager, which is not, I mean, I'd have to get into the kernel of the OS to do that, but if I had such a thing, I could take this out. Which is not so unreasonable. So in a sense, I could still say this is a linear time algorithm. But strictly speaking, it's not. It's got this extra thing in there. But I will call this linear time. Because I'm going to make the typical, I'm going to make a simple assumption that k is bigger than m. And k is bigger than n. We'll just make that simple. If we make that simple assumption that every row and every column has at least one non-zero in it, for instance, then this is linear time and linear space. Okay. So I know that's a lot of stuff. I'm not normally going to belabor. See, when I go into, I really am belaboring a lot of the details in this first chapter. When I get into some of the higher level matrix operations like matrix factorizations and forward backsolves and things like that, a lot of these little details of little tricks like this, I won't spend so much time. I'll mention them, I'll show you to them, but I won't spend so much time pointing out exactly why this works. I'll give you the gist of the idea, then you can look at this and realize, oh, I see what's happening. But I thought it's important at this level to go through some of the mechanics, because those sort of ideas, those sort of tricks will apply all the way through. And to get across the idea that, for instance, that we cannot never do this. We can never do order mn, or we can never do n squared. We always want to focus on algorithms that do this. And we really like to try to avoid logarithmic time, too. Because, I mean, log of 1 billion is still, can be a big number. Okay. So we're soon here now to get into actual linear algebraic functions, but the next thing I want to look at is we look now at how to remove duplicates, but MATLAB doesn't like hard zeros in the matrix, doesn't like explicit zero entries. Or you may have a case where, okay, I'd like to take my matrix and I want only the lower triangular part, let's say. Or I want to delete entries in the upper triangular part. Or I have a matrix and I want to delete small values, less than 10 to the minus 15 or something, some tiny values that all those should just be 0, and let me save the space by throwing them away and calling them 0 and not even storing them. Or whatever. Okay. And so that's what this function does. And the name actually is called fkeep, because what it really does is it keeps the things you want to keep and then deletes everything else. And the way this algorithm works, it's in some ways similar to this duple function. That's why I have it just after it. Because, it's going through the columns one at a time, and it's applying a predicate to that, which is passed in by a function pointer. Okay? And if this predicate says, oh yeah, I pass this predicate a row index, a column index, the numerical value, and then a void pointer, which this function doesn't look at the void pointer. But the void pointer is useful if the caller wants to use this function to say, look, I want to drop all entries that are smaller than 10 to the minus 10. This function doesn't see the 10 to the minus 10. I don't want to pass in an extra parameter, 10 to the minus 10, because then this thing would become more specific. But I want it to be generic. So I pass in the function, and the only thing I do this, use this void pointer for, is I pass this other stuff, which this function doesn't need, but maybe the fkeep comparator function or predicate function does need. So I take hit and pass it for this. That's all. Just like QSort does, actually. So if this is to be kept, then this, if I have numerical values, I compact it. And otherwise, and then I keep that row index in that numerical value. Otherwise, I throw it away. Don't sum it into anything or anything like that, but I throw it away. But so this has a very similar feel to the last algorithm, where I keep track of where the I record where the old column starts, and I keep track of where the new column starts, because I'm throwing things away. So things are compacting, like they are here. And I didn't need to keep a P of J. I guess I could have put this at the... I didn't need to keep Q or compare with Q, so I just did this at the top rather than at the bottom in the previous algorithm. And then this piece is like the second part when you see a new entry that's not a duplicate. Okay, so if you compare these two functions, you can see a lot of similarities between them. This part down here, okay, is the same as this part down here. I guess, except I wonder why I did this. The duple function requires... Why did I do that? That's really weird. This duple function assumes the matrix has numerical values. If AX is null, this will segfault. But you may have duplicate row indices in a matrix that's just a pattern, a binary, no values are stored. So I don't know why I did that. That's really strange. I should fix that. I should have a little guard here that says, if AX, do that. If AX, do that. That would be better. Whatever. Okay, so dropping entries from the matrix. And so then if I want to drop zeros from the matrix, I just do this. I create a function that returns true if the value is non-zero. And so then to drop zeros, I just call this function CSF keep, passing it to a pointer to this function. So this function right here then, and then I don't need the void star thing, so I pass null. So this would be how to drop zeros from the matrix. I call fkeep, passing in the @cs non-zero, which is this little function here. If I want to drop small entries, then I could pass in this function as a pointer, which it computes the absolute value of the entry, and if it's larger than the void pointer typecast to a double pointer and then extracted to get the tolerance, okay, then if I keep it if the absolute value is larger than the tolerance. And so to drop tiny entries, I just do this. So it's a very flexible kind of function. Then you can do all. And if you wanted to drop entries in the upper triangular part, then you'd have a function here that would compare I and j, and return true if I is greater than or equal to j. And that would keep the lower triangular and drop the upper part, and so forth. You could imagine all kinds of different ways, predicates on entries that you want to keep or delete, and that'll do it for you. Okay, and now I have 2 minutes left, which is not enough time so much to get into the details of the next topic. But now we're getting into more of, so far we've seen just a lot of sparse matrix algorithm mechanics, how to manipulate this data structure. Now what I want to do is start looking at more interesting numerical algorithms, which is what we're driving at anyway. And the first one is matrix multiplication. And matrix multiplication is a very interesting problem because for several reasons. First of all, we do need to adapt this algorithm properly to our sparse matrix data structure. All right. Let's suppose I have two n by n matrices. All right. A and B. Now, if you use the conventional method for multiplying two matrices together, you would take dot products of the ith row and the jth column to get the Cij entry. So what would be the omega time complexity of this algorithm? The lower bound. And no, it's not n cubed. Omega n squared. Because you're doing n squared dot products. Each dot product might take constant time. I mean, you could imagine transposing A and storing it by row. Okay. So if you did this with a pile of dot products, guess what? We're back to Devia's desire to have an order mn. No, you can't do that. See? It's order mn. That's not good. So we can't use n squared dot products. We have to use something else. And that's what we'll talk about next class.